This is a sequences question, and if we look at the sequence, look at the patterns, we can see there's you've got these two sort of squares either side, top and bottom, that seem to be there constantly, and then we have a separate section which is a 1 by 2, 2 by 3, 3 by 4. So we can expect to have something similar. We can have a 4 by 5, and then the extra squares top and bottom. And with this question, to be honest with you, the best way of any question that involves the sort of shape patterns is to try and see if you can break down the shape. So here we have this idea that whatever my n term is, okay, so here I've got this 4 by 5 plus the 1 plus the 1. Well, that's to some extent what's going on. You've got your n multiplied by 1 more than that, and you're adding on 2, and that's the formula. We've actually answered one of the later questions in this. Now, there's another way of looking at it, and if you break down the shapes, I'll draw on top of the original drawings. You've got a square of 1 by 1, 2 by 2, 3 by 3. You've got your initial squares above and below, which makes your 2, adding on 2. And then here at the side, on the left hand side, you've got a 1 by 1, a 1 by 2, a 1 by 3. So we can imagine that my square, 1 squared, 2 squared, 3 squared is n squared. I have the 1 by 1, 1 by 2, 1 by 3 is basically adding on one lot of n, and I'm adding on 2. And that's another way of imagining the pattern. Now, whether I open up the brackets on my first sort of way of solving it, you'll see that I get the same answer. And if I were to do the question later on in a more formal way, you'll see that I get the same answer again then. But your life is made so much easier if you can see what is happening with the shapes, break the shapes down right at the beginning, rather than trying relying upon some algebraic processes. So if we go through completing the table, we've got 4, 8, and 14, and then the shape we've just drawn, we have 22 squares. Now, to continue on with this pattern, to some extent you have to understand what's happening with this. And to do that, it's worthwhile sort of thinking about what's going on with the pattern. So here we are adding on 4. Here we're adding on 6, adding on 8. So we can take it that we're going to be adding on 10. And then we're adding on 12. And then we're adding on 14. Now, there's a variety of different ways which you could have done that. You could have just sat there and just drawn all the other drawings and count up the squares. That's why I'm coming up with that, the rest of the sequence. You could have seen the sequence, come up with your nth term expression, and just substitute 5, 6, and 7 into the formulas that I just showed up above. You would have got the same answers. In terms of showing that the number of tiles in each pattern forms a quadratic sequence, the key thing here is if you look at the differences and see what's going on with differences, you're adding on 2 each time to the differences. Now, it's not fair that they've not really given you enough space to show this, to be honest with you. They should have done. This is the appropriate way of looking at the pattern, just try and seeing the patterns in the differences and the second level differences. So, second level differences are constant. Okay, so that is your sort of key understanding of a quadratic sequence. Part 3, we're asked to look at how to describe the number of tiles needed to turn the fourth pattern into the nth pattern into the nth plus 1 pattern. So any pattern you've got, how do we turn that 14 into 22 or this 32 into 44? how do we turn it from one term to the next? Okay, so you can see here, if you look at the green numbers, 4, 6, 8, 10, 12, 14, we add on 4, we add on 6, we add on 8, add on 10. They're the numbers that they're interested in. So if we think about those numbers, I have a sequence of numbers. It's a linear sequence because it's going up by 2 each time. I'm adding on 2 each time. So what sort of sequence adds on 2 each time? Well, the 2 times table. And if you think about it, the 2 times table, if I have the 2 times table, and I add 2 to each of those, I get those differences that are going on there. So those differences, 4, 6, 8, 10, 12, are the 2 times table plus 2, i.e. 2n plus 2. You can use other methods to get that formula. You can use this classic sort of formula for an arithmetic sequence, and which is in the formula tables, and where your first term a is 4 and your common difference is 2, and just substitute them in and you get the same answer. 2n plus 2 is the expression to describe what's going on there. And if you think actually about what's going on, looking back at the table, the number 4, the number 4 adding on to the first term to get the next term. Okay, 6 adding on to the second term. You could think about those numbers. What have we got there? Okay, 2 lots of 1 plus 2, 2 lots of 2 plus 2, 2 lots of 3 plus 2, 2 lots of 4 plus 2 gives you those numbers. For this next part of the question, all you're effectively expected to do is plot the information that you worked out in part B from your table. So we'll start adding on our scale, and since for the seventh one we wanted the number 58, well, to be able to do that we need to be able to fit 58 in here, so you can see these markers here. It would be appropriate that they were 10, 10, 20, 30, 40, 50, 60. Then we have a situation where we were able to fit on the seventh term. So we have up the side, we have multiples of 10, and then we can plot our points. So we're going to have 4, and then 8, and then 14, and then 22, and then 32, and then 44, and then 58. And you'd be expected then to, well, you don't necessarily need to actually connect up in between, because it's a step thing. Actually, there's not actually a continuous sort of drawing through this. Okay, you don't have the 3.5 term to know that there's going to be approximately 17 or 18 tiles. It's a bit of a nonsense, really. You do not need to actually connect those points. And there would be argument to say, well, you could do a bar chart where you've actually got these sort of bars actually coming up. Okay, there should be no issue there. Certainly there wouldn't be a requirement to do one particular graph rather than another. The key thing, they're expecting to see that sort of curve shape. Moving on to part D, well, we've already discussed this. We're being asked to come up with the nth term expression, and I've already shown you 2 ways of doing it, and I'm going to show you another again, just understanding the pattern, the sequence of numbers, and understanding how they're broken down. So we have our sequence. We're being told that it's n squared plus something n plus something, where b and c are numbers that are fractions. So, or well, they're rational numbers. They could be whole numbers, but they're nothing too difficult. So they're giving us the fact that it's n squared plus something, so we're not even having to work it out. Now, very quickly, if you had to work out your coefficient of n squared, all you would need to do is look at your second level differences. In this case, it's 2. And whatever your second level differences are, you divide by 2. Okay, and you get your answer. So whatever the second level difference is, divide by 2, and you get your sort of a, your coefficient of the n squared. But they're telling us what it is. Okay, they've told us it's n squared, so that's 1 squared, 2 squared, 3 squared, 4 squared. So the rest of it, bn plus c, Let's use a different colour. Must be the rest of it. So if I'd have to add on 3 onto 1 to get 4. I'd have to add on 4 onto 4 to get 8. I'd have to add on 5 to 9 to get 14. You can see what's going on here. We're going to have to add on 6 onto 16 to get 22. All I'm doing is I'm finding the differences between these two numbers, basically. Difference between 32 and 25 would be my next number, which would be 7. So I realised very quickly that this bn plus c, well, what's going on with it? Well, we have it's going up by 1 each time. So it's the 1 times table. So if I broke this down, it'd be the 1 times table, and I'm adding on 2 onto it. So the 1 times table is 1n, and I'm adding on 2. So just by breaking it down, so I have my n squared section, and I have my linear section, my times table, and I have my constant. So it's n squared plus 1n plus 2. Very little algebra, no algebra needed in a sense at all. I'm not having to solve simultaneous equations or all that sort of stuff. I'm just breaking down my sequence into parts, into the sort of squared part, into the times table part, and the constant part. And just for completeness sake, since it asks us for the value of b, well, b is 1, and they asked us for c, c is 2. And whatever formula you actually come up with, they're just wanting the 30th term. So the 30th term is going to be just substituting 30 into that formula that we found. And you just work that through. And oh, by the way, just as one final aside, I'm looking through the mark scheme written by DEB exams for this question, and they got part D completely wrong. They went and used algebra, they made some basic mistakes, and it just threw the whole thing out. Okay, now none of my 3 methods that I went through to get n squared plus n plus 2 did I make any mistakes, because I'm just looking at the basic structure of it. I'm seeing the patterns, and by virtue of the patterns being there, I'm not making any mistakes. They in the exam mark scheme, they blindly went through an algebraic process. They made one mistake early on, and the whole thing was thrown out completely, and they get the completely wrong answers for part 1 and part 2. Okay, so just and that's supposed to be someone who knows what they're doing. It's easy to make mistakes. Looking at the patterns, looking at the structure, going back to basics, you're far more likely to get the right answers.